Okay, let's see an example of quotient rings. Now that we have the first isomorphism theorem, I have quoted it on the right hand side here, and also there is an even shorter summary of the quotient ring construction on the right hand side up here, if we need to refer to them. So the only example that we have seen so far is that when, so let me just say again what we have here. So if you have a ring R and an ideal I, then R mod I is the set of cosets, the set of sets of this form, A plus I, where A plus I means all elements of the form A plus X, where X varies over I, for some element A in R. Here, A in R. So you look at the set of cosets, and you defined two operations called plus and dot on this set of cosets. And the way this plus and dot works is that when you add a coset of A and a coset of B, you get the coset of A plus B, and similarly for the product. And with these operations, this set R mod I forms a ring. The zero of the ring is the ideal I itself, so that's the coset of 0. 0 plus I is I. It forms a ring that's called the quotient ring. And you have this natural on-to ring homomorphism from R to R mod I, taking an element A of the ring R to the corresponding coset A plus I. It's called the quotient homomorphism. Okay. So the only example we have seen is when R is Z and I is NZ. So fix some natural number n, 3, 5, 17, 18, whatever. We know that every ideal in Z actually looks like this. So this just means all multiples of n, right? Take that ideal, then if you do the quotient ring construction, what you get is literally what we had called Z mod n earlier. So this notation Z mod n was anticipating this definition Z mod nz. And the addition and the multiplication on Z mod nz is nothing new. It's the addition and multiplication that we know and we have used pretty heavily in studying divisibility problems on Z mod n. Example 2 on my list is already something somewhat non-trivial. It's a rather special example, but so if you recall, we had this ring when we talked about rings a long time ago. We had this rather curious ring. The underlying set is just R2, R cross R, so points on the plane. With usual addition, just addition of vectors, but a curious multiplication, and multiplication defined by this formula. If you give me two elements of S, so they look like A comma B and C comma D, where A, B, C, D are real numbers, then to multiply them, you multiply the first components, and on the second component you do AD plus BC. And this is for all A, B, C, D in R. Or I could say for all pairs in S. And we verified that this is a ring, and this is a ring, in fact a commutative ring, with 0 being the element 0, 0, and it has identity. The 1 is the element 1, comma 0. Okay. What I'm going to do is I'm going to define a function. So here's the key. Definition. What I'm going to do is I'm going to define a function from polynomial ring in one variable over with real coefficients, just one variable polynomials, to S. This is going to be a surjective ring homomorphism, and then we'll apply the first isomorphism theorem to identify S with a quotient ring, Rx modulo some ideal. So define a map right now from Rx to S by alpha of a function. So an element of Rx is a polynomial function, right? So if the input is f, then the output is going to be the value of the function at 0 and its derivative at 0. That's a pair of numbers, right? So for example, if you give me the function x cubed plus 2x, then I'll take it. The value of the function at 0 is, or maybe, minus 1. Then the value of the function at 0 is minus 1, and its derivative is 3x squared plus 2, so the derivative at 0 is 2. Yeah, that's the map I'm looking at. The claim is twofold. First, verify that alpha is a onto ring homomorphism. The addition is clear, that if you add two functions and apply alpha, then you'll get the sum of the corresponding things. But you really need to check that the multiplication is preserved, that alpha preserves multiplication. So multiplying two functions and then applying alpha is same as applying alpha and then multiplying in the ring S. But the multiplication in S is defined to make this work. If you look at this formula, and you'll need the product rule for differentiation, you know. Yeah, if you remember the product rule, this implies, I'll just say, product rule, I mean this one, from calculus, and the multiplication law, multiplication of S imply that S preserves, not S, alpha, that alpha of a product is the product of the alphas. So that's what all I'll say about claim 1. The main thing is now claim 2. And it's rather straightforward to check that it is onto. I won't bother about that either. So this is an exercise, the rest of this, claim 1. What I need to do is to identify the kernel. You see, because first isomorphism theorem says, look on the right bottom, if you have a surjective ring homomorphism, which we have here, alpha, then the domain modulo the kernel is isomorphic to the image. So the claim 2 is that the kernel of this surjective ring homomorphism that we just defined is all multiples of x squared, the ideal generated by x squared. And once we have this claim 2, this implies, by first isomorphism theorem, that Rx mod x squared is isomorphic to this ring S, which looked rather strange in the beginning. So this multiplication law that we had up here is nothing but the multiplication law of this quotient ring in disguise. So let's see why claim 2 is true. So proof of claim true. You take something in that is a multiple of x squared. So take g, which is a multiple of x squared. Then how does g look like? G looks like x squared times some polynomial. Which means g of 0 is 0 and g prime 0 is also 0 because g prime x now is 2x hx plus x squared h prime x. So if you substitute x equals 0, you again get 0. So alpha of g, which is g of 0, g prime of 0, is 0, 0, which is the 0 element of the ring S. So what does this prove? This proves that all multiples of x squared are indeed in the kernel of alpha. Conversely, let's take a polynomial fx, or maybe g again. Write it like this. And assume that it's in the kernel of alpha, right? What does that mean? That means g of 0 is 0 and g prime of 0 is also 0. But what is g of 0? If you evaluate this function at 0, you get a 0. And if you differentiate this function, you start with a1, and if you evaluate at 0 then you get a1. So what you get is that if g is in the kernel of alpha, then a0 and a1 are 0, so gx is, it looks like this, x squared times a2 plus a3x cubed plus da da da. So it's really a multiple of x squared because the first two coefficient vanishes. So this is a multiple of x squared. So that proves the other inclusion, that the kernel is a subset of x squared. So that shows claim 2, and that proves Rx mod x squared corresponds, is isomorphic to S. And what is this isomorphism? If you give me a comma b here, that corresponds, if you unpack this proof, to the coset of a plus bx. Okay. So these are sort of degree 1 Taylor polynomials, if you will. And in here you can notice that if I write x bar equals the coset of x, then this element can also be written as a times 1, and 1 bar as the coset of 1. And this can also be written as a times 1 plus b times x bar. And notice x bar square is actually 0. This equality holds in this ring, in this ring T. Yeah. So that's like adding an infinitesimal element whose square is 0. So that actually implies the multiplication law, that if you multiply with c times 1 plus d times x, then you get ac plus ad plus bc times x bar, which was the multiplication law we had